Lesson 1.4 is polynomial functions and the rates of change. So the formal definition of a polynomial function, it says a polynomial function p of x where n is a positive integer and the coefficients a sub n all the way down to a sub 0 are real numbers, but a sub n is not equal to 0 is given there. It looks weird, but guys, you know what a polynomial function is. It could be a linear function. So we could have said p of x equals 3x plus 4. That's a polynomial function. It could be a quadratic function. So negative 2x squared minus 7x plus 1. It could be a constant function. So p of x equals 12. All right. Those are all polynomial functions. Could be a cubic function, a quartic. Could be any of those, okay? All right, the big thing, though, is here. Remember, a polynomial has a degree n. N is your largest exponent, okay? So the degree is the largest exponent. So like this first one that I did, the linear, my degree would be 1 because of that x to the first. The second one, my degree would be 2 because of the x squared. The third one, it doesn't have an x, but that's the same thing as having an x to the 0, so it would be a degree of 0, which is actually what this last one talks about too. If it's a constant is also a polynomial function with a degree of 0. All right, so let's focus on 1 and 2 here though, okay? So we have a linear and we have a quadratic. Linear has a degree of 1, quadratic has a degree of 2. The leading term is the term that contains that largest exponent. So most of the time when we write them, we put them in descending order of the exponent. So it's the one that's leading the function, leading the equation. So like for this first one, it would be that 3x. For my quadratic, it's the negative 2x squared. Not because it's first, but because it has the largest exponent out of all the terms in that polynomial. Now a lot of times they'll switch it up though. They'll move it to the middle and try to confuse us, so be careful. So the degree is n. The leading term is the term that has that degree as the exponent. And the leading coefficient is the number in front of that x to the degree. So for example, on our second one here, my leading term is going to be that negative 2x squared. The degree is 2, and the leading coefficient is negative 2. All right, let's look at example 1. So example 1 says, for each polynomial, identify the degree, the leading coefficient, and the leading term. All right, so on A, first thing I'm going to do is go find that leading term because everything else is contained in it. So I'm going to go find that largest exponent, which is this term right here. So there's our leading term, negative 5x to the 4th. Remember, the degree is going to be the exponent on the x, and the leading coefficient is the number in front of it. So for B, let's go find that leading term. Now be careful because this one's not in order, but there's our largest exponent. So 2x to the 5th is our leading term. And just think about if I told you to put this in descending order of the exponents, that's the one you would write first. Okay, so I know my degree then is the exponent 5, and my leading coefficient is the number in front of that x to the 5, so a 2. All right, and then that last one. Ooh, that one's a little tricky, right? Because now we have to work it out, but we don't have to multiply them all out. Multiply your x's, your largest x in each one. So I know I have just a single x right there. Inside the first parenthesis, I have an x squared. Inside the second parenthesis, I have a 10x. So when I multiply those together, x times x squared is x cubed times 10x is 10x to the 4th. That's going to be my leading term. And so I know my degree then is that exponent 4, and the leading coefficient is the number in front, 10. All right, let's talk about extrema. What are extrema? Extrema are like your maximums and your minimums. And so we have two types. We talk about relative or local extrema, and then absolute or global extrema. Okay, relative or local are maximums or minimums between 2 points. So really what we're looking for here, if we're looking for a relative or local minimum, is we're looking for a valley. And if we're looking for a relative or local maximum, we're looking for a hilltop. So let's go ahead and just look at the graph there below it. And so it says, do we have any local minima or any local maxima? Well, minima, remember local minima, relative minima is a valley. And I do have a valley right there. And so that's going to be at the point 2, negative 4. So it just asked me though for the x value. So the x value here would be 2. Now if it asks me for the local minima, not at x equals, just what is the local minima, it's usually typically just asking you for the y value. So anytime they do that, you'll see it all write out like my local minima is -4 at x equals 2. That way, if they were by chance asking for the ordered pair, I gave them all the information. It's still there and they'll accept it. And if they just wanted that y value, they really just wanted the minima, they also got that as well. All right, and then the local maxima. Remember, we're looking for a maxima. We're looking for a hilltop. Do I have a hilltop? I do, right there. It's the top of the hill. And then that is actually at what, -2, 4? This is just asking me for the x value, though. It says the local maxima at x equals -2. But if they wanted it, I would put it at a local maxima of 4 at x equals -2. All right, then they talk about absolute or global. When they're talking about absolute or global extrema, they want to know what global is, the big picture, right? Well, absolute, kind of same thing. I want to know what is the absolute maximum or minimum of that function. Not just hilltop or valley, the very top point or the very bottom point, okay? So when I look at this function they give us here, notice the way they set it up. This is what I was talking about on that other one there. They want to know the absolute minimum. So does this function have an absolute minimum point? Remember, minimum is a bottom. It has an absolute bottom point right there. Its ordered pair is 2, -4. So this one says it has an absolute minimum. The absolute minimum is, it's going to be -4 at x equals 2. You do not write it as an ordered pair. Write it out separately. All right, what about the absolute maximum? Is there an absolute maximum value of this graph? Means the very top point of the graph. Well, our graph keeps going. So there is no top point, so we would just put none. All right, if our graph ended, we would find wherever that top point would be, and that would be our answer. All right, continuing on. Example 2. It says for each polynomial, use technology to graph the function, identify whether it will have a global maximum, a global minimum, or neither, and explain how you know. Then find all extrema. All right, so when I go through and I graph this, and I'm just going to do a quick little sketch of it, okay? So it's going to look something like this. Okay, so I put it in my calculator, go to graph, here it is. And it wants to know if we have a global maximum or a global minimum or neither. It didn't ask about the local on this one, okay? So we're just asking about global. So do I have a global maximum? Do I have a very top point of this graph? I do not. Do I have a global minimum? A very bottom point of this graph? I do. And it's right there. Now, using your calculator, you look at it and it's not an exact pretty point. So I can't just say, oh, that's at -2, -1 or something like that, okay? I need to find it. So remember to find it. You can go to second, trace, which is our calc button, because we're going to calculate the absolute minimum here. You're going to find where it says minimum and choose it. And when you do that, it says left bound. So you want to move your cursor over here somewhere to the left of that point we're looking for. And then it says right bound. You're going to go to left bound and click enter. And then it says right bound. So you're going to go over, you're going to right arrow over somewhere on the right side of it and hit enter. And then it says guess. We don't care about guess, and hit enter. All right. Rounded or truncated to 3 decimal places. I find its ordered pair is -0.593. And its y value is -1.623. All right, so find all extremo. So this one has a global, or I could have put absolute, but they said global, so I'm going with global. Minimum of the y value, negative 1.623, at x equals the x value, negative 0.593. All right, now let's look at B. All right, we're going to put B in our calculator. We graph it, and it looks something like this. Now, depending on how tight it is or how tall they go and stuff, that just depends on what your window is, okay? This is just, and it's my drawing. If you haven't been able to tell already, I cannot draw very well. I do my best, and that's what I ask out of you. Okay, so my graph is going to look like this, and it's asking me, do I have a global maximum, a global minimum, or neither? Well, do I have a very top point? Nope, so no global maximum. Do I have a very bottom point? Oh, it keeps going down, so no global minimum. So this one is neither. Now, the explanation for this one, I didn't do the other one, so we're going to have to go back and talk about it. So when we go to explain these, okay, the easiest way is kind of to think about what you know about even and odd functions. And I can't recall how much y'all probably talked about this back in Algebra 2, okay? So let's talk about like this last one. This last one is what you call an odd function. How do you know it's odd? Well, one thing, because its degree is an odd number, okay? The degree on this one would be 3. All right, and because that's an odd number, that means this is going to be an odd function, okay? An odd function is like, think about one you know really well. Y'all are kind of familiar with cubics, but what about a linear, okay? An odd function is like a linear function. They're always going to, the end behavior, what's on the far left and the far right, is always going to go in opposite directions, okay? So if it's an odd function, there's not going to be any global minimum or global maximum. The other type is if we have an even function, and an even function has an even degree. So if you look at A, notice its degree is 4, okay? And so compare that to another even function that you're pretty familiar with, a quadratic that has a degree of 2. You know a quadratic, if it's positive, it's going to open up, and if it's negative, it's going to open down, okay? So you know that it's going to have either a global maximum if it opens down or a global minimum if it opens up. So when I look at A, since I'm there right now, I know that it's an even degree and it's positive, which means it's going to open upwards. I don't know what's happening in the middle, but I know that it's going to be opening upwards. So the ends are going to be going like this, which tells me there I know I'm going to have a global minimum. So here we could add in here is a global minimum, blah, 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 because j of x, the function name, is an even function. Now for B, remember justification, anytime it's an odd function, it's not going to have either. It's not going to have a global maximum or a global minimum. So it's neither, because k of x is an odd function. All right, we'll talk more about even and odd functions later. All right, points of inflection. We've already talked about these, even though they hadn't formally talked about it in the notes or anything. A point of inflection occurs when the polynomial function changes from concave up to concave down, or from concave down to concave up. Points of inflection of a polynomial occur at input values where the rated change of a function changes from increasing to decreasing or decreasing to increasing. All right, so if we've got some function here, all right, we know that this first part right here is concave up. But somewhere in here, it's going to change so that this becomes concave down. And we've talked about that point where it changes in here is called your point of inflection. A point of inflection will always occur somewhere, usually, well, it's about halfway between a relative maximum and a relative minimum value, okay? So if you have a hilltop and a valley, you're going to have a point of inflection in between them. So if you look at this one that I just drew on there, has 3 minimum or maximum values. 1, 2, 3, which means I'm going to have 2 points of inflection. It's always one less than the number of maximums or minimums, because you got a point of inflection between what I labeled 1 and 2, and you're going to have a point of inflection between what's labeled as 2 and 3. Remember, there are going to be points where that concavity is changing. They're the points where that average rate of change is changing from where it's increasing to decreasing or decreasing to increasing. All right, so moving on, example 3. This is a graph of the polynomial function y equals g of x is shown at the right with 5 key points identified a, b, c, d, and e. Identify the x-coordinate of any points of inflection. All right, so where are our points of inflection? Well, for one thing, I can see I have 1, 2, 3 little minimums and maximums, which means I'm going to have one less than that, so 2 points of inflection. They're going to happen approximately halfway between those maximum and minimums. So between points A and C, I have a point of inflection at B. So x equals B. And then between C and E, I've also got this point of inflection at x equals D. All right, some more polynomial information. So it tells us here that between every 2 distinct real zeros of a polynomial, there must be at least one local maximum or one local minimum. So remember, the zeros, real zeros of a polynomial, are the x-intercepts, okay? They're the zeros, x-intercepts, roots, solutions. All right, so if we have 2 zeros here, I'm just going to pick 2 on this graph. If I can get my pen to work right for me. Zeros are your x-intercepts, okay? There has to be a maximum or minimum in between it. And hopefully that makes sense, because when your graph goes through it, it's got to go somewhere to turn around. So like this one turns right there. Or this one here will turn down here, okay, before it gets to the next one. So there has to be at least one local maximum or local minimum, depending on the graph. All right, polynomial functions of even degree must either have a global maximum or a global minimum. We talked about that. Even degree, it's going to either open up or open down, so therefore it has to have a global maximum or a global minimum. We'd already talked about it. All right, putting it together, example 4 says for the function y equals g of x shown at the right, identify the characteristics. Known values for g are shown in the table below. All right, so look at the domain. Domain, remember, is your x values. So as I look at this graph, I'm looking from left to right. Well, I notice my graph is going to keep going up towards the left, so it keeps going left. It's going to go up towards the right. It keeps going to the right. There's no holes, no gaps, no jumps in between those end values, so it keeps going in both directions, so negative infinity to infinity. My range, remember your range is your y values. Y values go up and down. So I can see here that my graph keeps going up, whether you look at that side of it or this side, keeps going up, but it does not keep going down. So we're going to go find that lowest point right there. And let's see if they told us what that value is for sure. It looks like 1, -8, but I can see here that we go a little bit lower, right? So we go down to -8.1. So we're going to, it goes down to -8.1, and it's going to keep going up to infinity. Now at the -8.1, we're equal to it. So remember, put that square bracket and use a parenthesis next to infinity, because we can never equal infinity. All right, the type of function or degree. I'm going to come back to that in just a minute, because let's talk about the zeros because the degree tells us how many zeros there are total. So if I can go find my zeros total, then I know what my degree is for sure. All right, so remember zeros are the same thing as your x-intercepts. So when I look on here, I can see 1, 2, 3 x-intercepts. Now I just told you the total number of x-intercepts is the same as the degree. But this is not a cubic function because cubic function's odd and they're going opposite directions, okay, like linear does. This one's obviously an even function. But notice this one crosses through at a straight line. That one crosses through at a straight line. But that one looks a little weird. I don't know if you've talked about this or not. That's because that one counts for more than one. What shape, if we just look inside our circle, the part of the graph right inside that circle right there, what shape is that? It's an upside down U. It's a little parabola. It's quadratic. Quadratic is x squared. So that 0 counts for 2 of them. So where are my zeros? Well, my first one is right there at x equals, it's like -5. My last one is over there at x equals 2. But that middle one is at x equals -2, but we say it has multiplicity of, we said it counted for 2, so multiplicity of 2. So it counts twice. And so when I go to get my degree, so I'd say what kind of function this is, this one counts for 1, plus 1 is 2, and this one counts for 2, so the 2 already had, plus that 2 is 4. So this is a degree of 4. And it actually has a name of a quartic. If you don't know the name, just call it a 4th degree polynomial, okay? So you can do that on all of them. Linear, and hopefully quadratic you'll remember, but even quadratic, if you can't remember, you just go blank. It's a 2nd degree polynomial. Cubic is a 3rd degree polynomial. Quartic is a 4th degree polynomial. And then there's like quintic, and they have other names, but to be honest, I don't even know what they are. I would call if it was x to the 6th, if it has 6 zeros, then it is a 6th degree polynomial. Okay, let's keep going. So intervals where g of x is increasing. So as I go across this graph and I read it from left to right, I can see I'm going down here. So this is decreasing, which I'm going to go ahead and look at f because f is decreasing. So I'm going to do these two together. So I am decreasing from -infinity to this point right here, which looks like it's about at -4, -4. And when I look in the table, that point exists. So it's going to go to where x is -4. And then we're increasing. So we're going to increase from where x is -4. And we're going to keep increasing to right there, which is when x is, and that point's on there, -2. And then after that point, we're going down, so we're decreasing. So we're going to decrease from x is -2 to this point right here, which we said was where x is 0.9. And then after that, we're increasing from x is 0.9, and we continue to increase to infinity. All right, now on your notes, keep writing in your respective boxes. I'm going to write over here on the side and just kind of erase as we go through because I want to still be able to see my graph. All right, so G says we're going to find the relative maximum. So relative is local, so those are our hilltops and valleys. And so I can see I have a relative maximum right there. So we have a relative max of the y value 0 at x equals -2. That's G. H wants relative minimum. So relative minimum are going to be our valleys. And so I can see I have a valley right here and right there. So I have a relative minimum of negative 4 at x equals negative 4, and a relative minimum of negative 8.1 at x equals 0.9. Remember, this point right there is right there in our table. All right, what letter is that? Nope, that's J. They skipped I guess because it looks like a 1. Let me go ahead and erase this so I can rewrite up here. All right, so J wants to know where's the absolute maximum. Absolute, remember, means absolutely of the entire graph. So, but this graph keeps going up. So there is no absolute maximum. K wants to know the absolute minimum. Well, the absolute minimum is right there. It's the very bottom of the graph. So I have an absolute minimum of, that's that point in our table, negative 8.1 at x equals 0.9. L says how many points of inflection are there and how do you know? Well, remember, one way is we can count our little maximums and minimums. There's 3, and so we know the points of inflection are going to be 1 less, so we know that there are 2 points of inflection. All right, so we have 2 points of inflection. Since we have 3, and instead of putting maximums and minimums combined, I'm just going to call them turning points because that's where our graph is turning from increasing to decreasing or vice versa. Okay, M. Remember, you should be filling in your little boxes on your notes, okay? I'm just doing this so we can continue to see the graph. Otherwise, I can't see my graph. Okay, M is the intervals where g of x is concave up. Now, we got to figure out what these little points are, the points of inflection, which they could have asked us for that first, but they didn't. So we know that there's some point of inflection right in this area. And so I'm going to go look in my table and see if they give me a point between negative 4 and negative 2. And they do. They told me it's negative 3 and negative 1.8. So that is my point of inflection. Negative 3, comma, negative 1.8. And then the same thing here between negative 2 and that 0.9. And so they gave me a point right there. So that's going to be our point of inflection as well here. So right here. And it's got an ordered pair then of negative 0.5, comma, negative 4. All right, so go back to this. M says intervals where the graph is concave up. So I'm going to change colors. Let's go with purple. So I can see that this part of my graph is going to be concave up. It looks like a cup. And so I know it's going to start way over here on the left. Be careful. Remember, we're talking about x values, not the y's. It keeps going up, but it keeps going to the left where x is negative infinity. And to that point of inflection right there, which is when x is negative 3. All right, and then it's also concave up over here, so at that point of inflection, so from negative 0.5 to, there is no next point of inflection, it keeps going to the right, and to the right, my x's go to positive infinity. All right, and then N wants to know where it's going to be concave down. And so it's going to be concave down in this area. So from this point of inflection at negative 3, when x is negative 3, to the other point of inflection where x is negative 0.5. All right, and that is lesson 1.4.